Okay. Okay. All right. So welcome to the lecture that we're doing today. I'll attempt to give a lecture on composition, or sorry, I've done composition. I would like to do it on inverse functions and give some examples, hopefully discuss also one of the examples in the book. Okay, just let me check to see, is the sound working? Okay, it looks like the sound is working. Yes, okay. I checked that briefly. If you could let me know that you're here, just send something to the chat, please. And I'll be watching that if you have any questions. I'll just write something briefly there in the chat so that you know. Okay. So, let me just get the board erased. All right, so I have switched my location to a new location, so things might look a little bit different, but anyway, another's place. All right, so the last time we were looking at composition of functions, and I gave you an assignment. If you have any questions on the assignment, please feel free to write me and interact. And I should mention that as part of the grade, there'll be an attendance score. It's 5% of the grade, and the way that we are discussing or thinking about recording or measuring attendance is by your participation. So the more that you can write emails to me, ask questions, just let me know that you're following the class. And of course I'll see it once the assignments are completed, and I'm still working on completing the assignments, grading the assignment, the first one. So that turned out to be a lot more work than I thought, so it's still in the process. I finished one person's assignment, first assignment, and so I have yet to grade the rest. So anyway, that I don't want to do it that way. I want to do it by Maple now from now on, because it's a lot easier to grade and to get the homework back to you so that you can get feedback as soon as possible. Maple will do that a lot better. I'm still learning Maple as well. So, okay, so let's discuss or introduce the topic of inverse functions. Okay, can everybody see that? Let's see here. Okay, so we have a function here. Let's draw it on the x and y axis. And so it's something like this. So remember, a function is defined on an interval from a to b. Here b is negative, sorry, a is negative, b is positive along the x-axis. And then you have you have 2 points, let's say C and D, along the y-axis, and you can see that the domain of this function is between all the numbers, all the real numbers from A to B, including the endpoints. Okay, so the function is a mapping or a rule which assigns to each value along this interval the value of y, which you get by going directly up and reading off along the y-axis. So the range is going to be the set of all the values between C and D inclusive. Okay, so we're noting that A is less than B, C is less than D. So it'll be a typical, this will turn out to be a typical function for which you can take the inverse. All right. Let me just check things here. You can take the inverse. Okay, so it's working. All right, so then, now, what we need this function to be, in order to have an inverse function, so this we call y is equal to f of x. In order to find an inverse of f, and we call that function f minus 1. So it's like f to the power minus 1, but it's not taking the reciprocal. Here this means something different. It means the inverse function. So in order to be able to do this, we need f to be 1-to-1 on its domain. Okay. All right, so here's the domain of definition of the function f, right? On this domain, okay, so the idea of an inverse function is an inverse function of a function basically undoes what the original function does. So the original function, the idea of the original function takes a value of x. Okay, you put it into the box f, and out comes f of x. The inverse function should take this value and give you back x. All right? So the inverse function undoes what the function does. It gets you back the same thing that you started with. This x is the same as what you started with. Okay. I better watch my board here. Okay. So now, graphically what that means is you start with an x here, and you go through this function. The function tells you that the value of f of x is simply the y value here. Okay, so here's y, which is the output of this first step. This is y. F of x is equal to y. All right. And then the inverse function will basically take this value and just go in the reverse way. So you then end up, you're going to go this way first, and then you'll go backwards along this path. You'll hit this point, on the graph, and then you'll go down and get back to x. So that's what the inverse function does. So the way you would say it is x then is the inverse function evaluated at y, where y is this value. Okay, now in order for this to work, in order for this all to work, so you can write it like this: y is equal to the function of x, and this is equivalent to x being the inverse of y. Okay, so why must we? Under what conditions does this work? All right, in order for this to work, the original function, first of all, it has to be a function. So you get a unique value of y, or a single value of y for each value of x. And furthermore, if you go the other way, you need, for each value of y, there to be a single value of x in order for this inverse to be a function. So that's why, to say the same thing, you need the function to be 1-to-1 in order to get the inverse. All right. So we need this because f will only be a function when for each y there is only one x, which is the inverse function of y. Okay. So we need this. In order to get an inverse function. All right, now with these two properties, both holding, we can write down actually two different, they look very much the same, but they're different properties of the inverse function. The first property is just what I described here. If you start here at x and you find the function of x to get y, you end up here along this point, at this point on the y-axis. If you start at the x-axis, the inverse function tells you this is the point y on the y-axis. That corresponds to x. Then when you take the inverse function of that, you end up going back here, back along this path to x by this equation here. So putting that together, so that's the composition of the two functions, f first and then f inverse. Okay, so I'll keep that diagram. This is also a useful diagram here. So these are the two key properties of inverse functions. F of x done first, and then composed with f inverse, that's always equal to x. Okay, because this means f inverse of f of x. First I do f of x and I get y, according to this, and then I plug in y and I get this equation here. So that's one key property. The other key property is that you can go the other way. You can start with y and then you can perform the inverse function to get x, and then you can perform f on that and get back to y. So it's just reversing the order of the two functions. Okay. So then, in that case, you would get composition of the two functions in the reverse order acting on y is equal to y. Now we should be careful here, because this only works when x is in the domain of the first function that we use here. That's going to be ab. So that's the domain of the function f. This is true for any x in this domain. So you can see if I draw any line from the starting x, then I get to a y, and then I can go back again. Remember, domain of f is AB. All right. So these are just equivalent. So this thing's always true for inverse functions, and this is always true for y in for any y in the domain, or sorry, the range of f, which is CD. Okay, so I'm just rewriting. I wrote that down before, but now I'm including the important notation that this is the domain of the function f. These are the x values of the function f, and these are the range values of the function f. Or these are the input values of f. These are the output values of f. Okay, so in both cases, the composition of the inverse with itself, or the function itself with its inverse, gives you the identity, either on the domain of the function or on the range of the function. All right. So let's erase this. We're always going to be using, for finding inverse functions, we'll always require f to be 1-to-1. We'll see later that if we have a function which is not 1-to-1, we'll have to restrict it in order for it to be a function that's 1-to-1. Otherwise, we can't take its inverse. Okay. Well, what can we say about the domain and range of the inverse function? Domain of the inverse function now, I'm taking values along the y-axis. So those will be my new x values. All right. And then the inverse function will just take me back to along the x-axis here, and those will be my new y values. So I can see that the domain will be all the values, real numbers between c and d, and the range will be all the values between a and b, inclusive. So these were just the domain and range of the original function, but switched around. So this was the range of f, and this was the domain of f. Okay, so the inverse function has a domain which is simply the same as the range of the original function, and the range of the inverse function will simply be the domain of the original function. Okay. How do you graph the inverse function? So these are the domain and ranges of the inverse function. So graphing one? Well, this formula is true if y is equal to f of x. All right. And so again, the new x value will be the old y value, and the new y value will be the old x value. Okay, so the new x value will be simply y, and the new y value will be simply x. So I'm basically taking the y-axis now to be the new x-axis, and vice versa. The new y-axis will be the old x-axis. I'll just make it explicit here. These are the old. The old values of y become the new values of x. So this function, the inverse function now, okay, I could just think of this, I could think of it as prime. So x prime is equal to y prime is equal to x. So prime just is included here to make it, to just remind you that the x and y here are different than there. But sometimes we will drop the primes if it's clear enough. And sometimes you'll be asked to draw the function and its inverse on the same graph. So what will it look like? Well, here you have c starts about here, and d starts about here, or ends here. So you get c and d, the same real numbers as you had before, and then a and b lie along here. Okay, so you're starting down here, and you'll curve up and you'll go up to here. Okay, so it's looking like this. So that's curving slightly down, sort of has a negative curvature here, and this is sort of a positive curvature. Here it's curving down, here it's curving up. Okay, if I were to plot these on the same graph, then I will get, the old function will look like this. Here's c, and this will be a over here. So it looks something like this. So you can get one from the other by reflecting through this line here. This line is y is equal to x. Okay, and you get each point here. So if I give a point here x, y, then that will be that's the old function. Okay, here I'm dropping the primes now, so I'm just gonna think of these as two functions. So now for this function, I've simply interchanged x and y. Okay, in order to draw the graph along with the other function. All right, so now you can see that the point here, xy, will be switched and become yx here. Actually, that's okay. Yeah, it's a bit confusing. Here it's not really, it's still the old, I haven't interchanged it yet. So this is still saying y is equal to, x is equal to f inverse of y. So I have not interchanged them yet. So these, yeah, so I can still think of these as primed. So let's put back in the primes. Okay, so let's try to repeat that. I've drawn both graphs on the same axes, x prime and y prime. For any point on the original function, x and y, where y is equal to f of x, I will get a corresponding point on the graph of its inverse. Namely, just switch the order, yx. All right? And in this case, x is equal to the inverse function of y. So these equations, if one is true, then the other is true. All right? So switching x and y just is the same as reflecting about this axis here. So to get the graph of f inverse, reflect the original graph of f about the line y is equal to x. Okay, so that's graphically how you would get the inverse function from the original function. Okay, so let's see some examples here. Okay, good. Okay, so I see you are here. Good. Let me just check. Is the sounds okay still? Is the sound okay? Oh. Let's see here. Okay. All right. I didn't hear anything, so let me just check that. All right. I just wrote a message there. Okay. So yeah, okay, I can hear it, yeah. Okay, so just briefly I checked it. Okay, so let's do some examples here. Okay. Now the way to check whether one function is an inverse of the other is to use both of these properties. You have to show both of these properties are true. So you might be given, let's say, f of x is equal to 2x minus 1, and g of x is equal to x plus 1 over 2. Okay, so they're two linear functions. Okay, so show that they are inverse functions of each other. All right. Okay, so you need to show, so the solution is, you need to show first that f composed with G is equal to the identity on the domain of F, and the other way. G composed with G first and then F is also the identity on the domain of G. Now the domains are, in this case, all the real numbers, so domain of F is all real numbers. The domain of G is all real numbers. And so are the ranges, because these are straight line functions. Okay, so let's see what the graph would look like. Let's see what the graphs would look like here. Okay, so I get -1, +1, 2, 3, 4. -1, +1, 2, 3, 4. On the x-axis and y-axis, let's do an extra 1. And so this function will be the y-intercept of this function, right? This is recalling your Math 101 or Math 099. The x-intercept or the y-intercept is -1, slope is +2, so it looks something like this. So if I go 1 over, I have to go 2 up, 1 over and 2 up, so something like this. And that would be my plot of the first function. Draw it here somewhere. Should be a straight line. Okay. And then the second function has slope equal to 1/2, and the y-intercept is 1/2. So we should label these. So plus 1/2. Oh, sorry, here. This is plus 1/2. This is the y-intercept of the second function, and its slope is 1/2. So we'll go actually through this point. If you want to draw a table and just make sure that these are correct, you would get at 0 you get 1/2. So that's right there. 0, 1/2, and then this will be 1. 1 will give us 1/2 plus 1/2 is 1. So it will be here. You can go up to 2. 2, let's say, is 2 over 2 is 1 plus 1/2, so that's 3 over 2, or 1.5. So that's right here. Oh, sorry, right here. 2 gives you this point here. So if I go along 2, the slope is 1/2. So if I go along the x-axis by 2, then I go up the y-axis by 1. So the graph will look something like this. -1 will give me 0. All right. So the domain and range are, I should write the ranges down as well. The range is all real numbers for both functions. Okay, so there's no restriction now if I, they could well be inverses, because if I interchange them, then I get the same thing. If I interchange these two, it's the range. If I interchange these two guys, then I get just those two. Right? So that's equal to that, and that's equal to that. So they could be inverses of each other, because that restricts these domains and ranges are the right ones. Okay, so let's see explicitly how to do that. So you take the function f, you take the composition with g. So I take g of f, which is 2x minus 1. Okay. And that gives me, now I just evaluate this. This will give me 2x minus 1 plus 1 is 2x. Divided by 2 is, 2's will cancel and I get x. All right, so that's the identity function. The composition g composed with f is the identity here. That's true for all real numbers. Then I do the same thing in reverse order. So I take f, which is 2x minus 1, of the evaluation of g of x plus 1 over 2. Like that. And so again, you see the 2 here will cancel the 2 up here, out here, and you get x plus 1 minus 1, which is equal to x again. So again, they're both the identity. And so these are inverses of each other. Okay. Now looking at the graph, you can see how the two graphs illustrate this reflection property of inverse functions. If you draw this line, y is equal to x, you'll see it goes right in the middle of the two functions like that. Okay, so often I might ask you to, for practice or on a test or something, I might ask you to draw the two graphs of the function and its inverse, as well as the graph of y equals x. So you should be able to see that, you should be able to show that this line is a reflection of the other line. The graph of the function f is the inverse of g, and vice versa. So g is the inverse of f, and also f is the inverse of g. Because if you switch the two, the same properties will still hold. Okay, so f is the inverse of g, and g is the inverse of f. That's always true for two inverse functions. So in other words, f is the inverse of f inverse. Okay. So now let's look at another example where I will look at a quadratic function. Okay. So let's erase this. Okay, so let's do it in a similar way. So I take the function f of x is equal to x squared. So that's a quadratic function. That's our most simple quadratic function in our basic toolkit, right? And that we want to restrict the domain to be only positive x. All right, and that's important, and I'll show you why. And then you want to take g of x is equal to the square root of x, and the domain of it will be all real numbers that are positive or 0. So it's similar to this. It's the same as that. Well, here we need this restriction because otherwise the square root function will not be defined. So this you can understand right away. But why do we need this? So again, I'm gonna show that these are inverses of each other. Okay, so here's our picture again. And I'm going to graph the first function. So what the first function is saying is just plot the points along the positive real x-axis, positive x-axis. And we'll get something like this. Right, so this is a graph of the first function f, parabola. It's just half of a parabola. Yeah, didn't do that very well. Try it again. Okay, so this is y is equal to x squared for on the interval 0 to infinity. Okay, so I made this restriction. If I took all the real numbers, so this could be defined on all the real numbers, but for the purposes of getting an inverse, that will lead me into problems, because if I take this other half, right, which looks it's just a reflection about the y-axis of the other half, of the first half. If I take this, then I look on this whole range, on this whole domain, and I don't get a one-to-one function. So f is not one-to-one if the domain of f is all the real numbers. So that's why, therefore, choose the domain D of f to be 0 to infinity only, just the positive reals or 0. Okay. If I included this other half, then I don't get an inverse function, because I could go from x and get a y value for all the positive and negative values. But given a single y value, I don't know which way to go. I'll get two x values that will correspond to that. So I don't have a function there. It's not a function. The inverse function is not a function if it's not one-to-one. If the original function is not one-to-one. So f wouldn't exist as a function. If I don't restrict. If I keep the domain to be all the reals. Okay, so the idea is one-to-one functions, you can tell when something is one-to-one usually by by looking at the property. Is it always increasing or is it always decreasing? Okay, so in the original, if I take the whole real numbers to be the domain of f, then I can see the function decreases and then increases. Okay, so that would not lead to a good, that's not a one-to-one function, because if I go down and up, then I'll have two values of y the same. Or two x values will give me the same y value. Okay, so I need either to be going strictly down over that domain or strictly up over the domain. So I could actually choose the other way. So I'll show you in the next example, if instead of choosing the the right half of the parabola, I choose the left half to find the inverse of that. Okay, so now, once we understand why this restriction is made, okay, then the rest is straightforward. So let's keep it in mind, though. X always has to be positive when you plug it into this function f and get x squared. Okay, so let's see what we have to do. We have to take g composed with f of x. All right, and I have to get back x. So what is f? That's x squared, and then I have to take g of that, which is the square root of x squared. All right. Now you might recall that, okay, so if x is any real value, then if you square it and then take the square root, then you get the absolute value of x. Right? Because the square root always gives you something positive. If x is positive to begin with, then this, which it is the restriction. Then we get back x again. All right. All right. So this is why we get the first identity. X is positive. That allows us to simply evaluate this. This is true for all real x, positive or negative. But then we use the fact that x is positive to get that we can write it like that. This evaluates just to x itself. The other way, you first take the square root of x, and then you square that. Well, in order for x to be defined, we have to have it in this domain. So it's already positive, or 0. And so when you square this, squaring undoes the square root sign, and so you just get back x. So x is really, the square root of x is defined to be, as long as x is positive, it's defined to be the number such that when you square it, you get back the number that you started with. Okay, so again, that's true. So both identities are true, and as long as you have the restriction x greater than or equal to 0 for both identities. All right. So let's look at the other function just to show you the graph again. So the other function will be the square root function. It will be something like this. So you'll get the graph that looks like that. And again, it's going to be the reflection of the first graph about the line y equals x. So at any point along on this graph here, say this one, 2, 4, that gets reflected to 4, 2, which I have here. This point is 1, 1, 1. That's right there. And that's not moved at all by the reflection because it's right on the line y equals x. So that will stay where it is. You can see that I've drawn that line right through that point. And then you have other points along here. Let's say 1/2, 1/4 gets reflected to 1/4, 1/2 over here. Okay. All right. So now let's try a third example where I'm going to change the domain of f. I'm going to make it the negative real numbers are 0. Okay, so let's see what we get when we do that. Okay, so this will be example 3. What should be the function g of x there? Okay, I'll show you. That will be negative square root of x. So that's all we have to do to change the second function in order for it to be an inverse of f. Okay, so what will that look like on the graph? So we'll have to erase a bunch of this. This will be our new, I'll keep that here. That will be our new function f. Okay, because I'm drawing it now for negative real numbers only. I should get a graph. I should get permanent ink or something and make a graph that way. But okay, so that's going to be f y is equal to x squared for x less than or equal to 0. The function over here will be the negative square root. This will be the set of points here. So let's see why these two are inverses of each other. First, you can already see it from the graph. You can see that if you reflect all these points here, for example, you can just take sample points. This point is what? -1, 1. And it gets reflected to 1, -1, which is over here. So that works, right? And then 2, -2, and 4. That gets reflected to 4 -2, which is over here. So in each of those cases, those points do get reflected about this line to the other graph, okay, to points on the other graph. F is 1 to 1 because it's restricted to the domain where it's to this side where it's only decreasing. All right. So for each value of y, there's just one value of x, which will give you that value of y. Oh, by the way, if f is 1 to 1, then its inverse will also be 1 to 1. That's another note I have to mention before. F is 1 to 1, and its inverse exists, which we've been showing you all along, then G, or F inverse is also 1 to 1, and vice versa. If the function it exists at all, if the inverse function exists at all, then the original function has to be 1 to 1. Okay, so let's go back to this question. So I want to again show that the composition of G with F of x will give me the identity on the domain of F. So here I'm starting on the domain of F, so I'm taking any negative real number. So I have to take this expression here. G of x I put in x squared. Well, just as before, this whole thing in the square root is absolute value of x. Now this minus sign here is important because the values of x are always negative, so this absolute value sign evaluates to minus x. Okay, remember my piecewise defined way of writing the absolute value of x. It's equal to x if x is greater than or equal to 0, or minus x if x is less than 0. Here I can include 0 among these values here, because I get the same thing. If x is plus or minus, I still get 0. Okay, so this minus sign has to appear because x is negative. But the minuses will cancel each other, and I get x again. So this statement is, this composition of the two functions together is in fact the identity. Okay, if I go from -2, f takes me up to 4, and then f inverse will take me from 4 back to -2. Okay, so that's the nature of the graphical graphical way of seeing it. That identity. And the other identity, let me just erase this, write it down here, is f composed with g of x. And that is the square of minus the square root of x, like that. And that you can see is, when you square, the minus sign goes away, and you just get the square of the square root of x, which is again x. So that's true. And this has to be true for x positive, whereas this is true for x negative. Okay, domains and ranges. The domain of f is the set of all negative real numbers. Its range is the set of all positive real numbers, because it's all the values along the y-axis, which is the positive y-axis here. The domain of the negative square root it's g, is the set of all positive real numbers, or 0, and the range of g is, it's negative square root, so all the y values are going to be 0 or negative, so it's going to be in this interval. Okay, so you can see this is equal to the domain of f, and this is equal to the range of f. Okay. This was also true, by the way, for the first example. I'll let you check that. You can go back and check that if you wish. Okay, so we're at about 7 o'clock, or your time it's 7:30, so I'll go to about 8, or 1:45. So let's see, what other examples are there of inverse functions from our toolkit? All right, so okay, so we can write that. Let's say that is our function. Okay, so what is its inverse? Find its inverse. Okay. Now, here's a helpful property for finding the inverse. You would like to be able to solve an equation. Okay, so I write this as y is equal to x cubed. Now if I want to find out what value of x I get when I plug in a y, so usually you would think of this, the original function tells you if you plug in an x value here, you just take the cube and that gives you the y value. the inverse function should undo that operation. So given a y value, you want to find the corresponding x value. So what you can do, you can think of finding the inverse as solving for x as a function of y. And if I do that, I get x is equal to the cube root of y. Okay. And now since my new x value will be the old y value, I want to interchange this. Well, I could have done this earlier. I could have interchanged it right here. Okay, and then I solve for y. All right, and then I get the same thing. All right, so these two tell me what the inverse function should be as functions of x now. Okay, so this is a general way of doing it. If you have a y as a function of x, all right, and so y is equal to f of x, that function defines, that rule. So you're given an x and then you get a y. In order to get the inverse function, you interchange x and y, and you solve for y. And that will give you some functional form that are shown here. Okay, so here's the question. So this, from these two, get me to the point of saying, okay, let's at least try this. So let's see how it works. Okay, so we compose the two things in this order. So we give a value of x, and then we'll get, okay, first of all, the domains. Domains are a set of all reals, right? So this looks like this. Right, this is a function of y is equal to x cubed. Goes through the point 1, 1, and also minus 1, minus 1. And it's defined for positive and negative real numbers. So because this function is always increasing, it's going to be 1 to 1. When the domain is the real numbers. Okay. The inverse function is going to be defined on the range of that. The range of this function is again the real numbers. There's a place where, yeah, the graph is horizontal here, but it's if you take a horizontal line, that intersects the graph only in one point. Okay, so it still satisfies the horizontal line test for a one-to-one function. And so the range will again be all real numbers, and yeah, so the way you do this is you start with y is a function of x, you interchange x and y, and then you'll get x is equal to y cubed, and then solve for y, and then you get y is equal to the cube root of x. Okay, so check that. Okay, so this is another function, a new rule, which says whatever x I start with, it will be the old y. I just take the cube root of that, and then I get back y, which is the old x. So if I take x and cube it, and then put it in the cube root, okay, then I get x without absolute values now because I'm taking the cube root. So negative values of x will be allowed for that, and also the cube root of a negative number will be negative. And if I go in the other order, I first take the cube root of a value. Again, it could be any real number, and then if I take the cube of that, then I get back the original number. Okay, so both are true on the real numbers. Okay, so I've found, given a function f, I found the inverse f inverse of x, namely this. And I've also shown, I verified that it's an inverse function by verifying those two important properties. That f inverse composed with f is the identity, and f composed with its inverse is also the identity. So I could say that this function is the inverse of this one, and this one is the inverse of this one. Okay, so that means I have two basic functions in the toolkit functions, which are inverses of each other. Here's y is equal to cube root of x. So it looks like that. And again, this straight line goes right through all these points here. Where the function and its inverse intersect, that should always be at a point where y is equal to x. So I get this little, these sort of little beads there, it looks like. Okay, the domains are, in this case, always real numbers, domains and ranges. Okay, so that covers it for example 4. What is the inverse function of f of x is equal to 1 over x? Okay. Well, just put it in this form, 1 over x. This is defined for all x not equal to 0. If you look at the graph of 1 over x, y is equal to 1 over x, it looks something like that. So you can see it's always decreasing, although it does jump up from minus infinity to plus infinity here and then go down again. So it's decreasing everywhere. But most importantly, it's 1 to 1 by the horizontal line test. So if you draw the horizontal lines all the way down, they only intersect the graph in one point for all the points in the range. So if I interchange y and x, actually I just get x is equal to 1 over y, and actually when I solve I just get the same function again. So in this case, f inverse is just the same as the function that I started with. Okay, that makes a lot of sense. If I take the reciprocal of a number, and then I take the reciprocal of that number, I get back the original number. All right. So if I take f inverse of f of x, it's 1 over x, which is x. And doing it in reverse order, I get exactly the same statement. only restrictions are that x is not equal to 0 in most cases. Okay, so taking the inverse, if I reflect this graph about the y equals x line, oh sorry, that was 1 over x. If I reflect over the line y is equal to x, then I get the same graph. So this graph is symmetric with respect to interchanging x and y. Okay. Now I'll have some problems which I'll get to next time. For homework, or for practice I should say, work out the problem that I gave you in quiz 1 of last semester. Okay, I gave that handout and made it available to you. So please look at that. And I'll give you a problem set. I'll also try to give you practice problems from the textbook. Those aren't for handing in, but if you have problems, then you could come to see me about them. But you should be able to solve those problems as well as the ones that I'm giving you through Maple TA. Okay, and I also want to check to make sure that you're all able to get to Maple TA and access those problem sets. So far, some of you have done the assignment. That's great, but I'd like to see all of you being able to solve those. Okay, so that's all the lecture I wanted to give today, and just keep it a reasonable size. So the next lecture will be on the 10th of November, Thursday, November the 10th, at the same time, 6:30. Okay, so with that, if there are any questions, you can contact me and I can explain it later. So I see Zara was here, Ayman was here. Okay, so that's all then. So have a good day, and I'll see you next time on Thursday.